Alright, welcome everyone to Chapter 5. This is further applications of the derivative. Here we are in Section 1. This is maxima and minima, which are of course the plural of maximum and minimum, right? And so in this section, our goal is to be able to locate these things, locate maxima and minima using an equation, in calculus and algebra kind of combined. I know we have calculators, and the claim is, right, with a graph and stuff, it's pretty easy to identify a maximum or a minimum. So let me show you really quick what I'm talking about here in example 1.1. So this is our nice function, f of x, and I want to find where maxima and minima occur, right? So the plural, but in this case there's only one of each. So right here at, let's say, x equals 1.9-ish, our function f of x has a maximum. Okay, and then down here, maybe at x equals 5.5-ish, f of x has a minimum. So you can see when I say maximum or minimum, I'm talking about a y value, right? So here at the maximum part, this is the largest y value around, essentially. And likewise down here at 5.5, right, this is the smallest y value around. It has a minimum around that point. So let me talk a little bit about technicalities, right? Technically, when we say a maxima or a minima, we really mean a relative maxima and relative minima. That is, we say a maxima of f of x occurs at x equals whatever. So in this case, right, our maximum was up here at 1.9. If the function's value at c is greater than or equal to the function's value for all x near c. So this is the term kind of relative maxima. For instance, back here on this function, we can see that there are actually y values that are larger than this one right here, right? This y value you'd say is maybe around like 5 or something like this. Well, here's one that's, 17, here's one that's 25, right? So this is not the absolute maxima, absolute maximum, right? There are larger values over here, but it is a relative maxima. And so in this class, we're actually going to be saying maxima or minima. We really mean relative minima or maxima, right? So just kind of a heads up, we're going to abuse basically the way we speak just because it's a little bit faster. A minima of f of x occurs at x equals c if the function's value, nope, can't do that, need blue. If the function's value at c is less than or equal to the function around, so for all x near c. Okay, so it's the smallest thing around, again, just near c. Later on it could be smaller, like over here for instance, could be smaller, but around this 5.5, this is the smallest thing. Okay, now, so again I said, if you're given a graph, finding minima or maxima is easy. We would like to be able to transition about using an equation along with some calculus knowledge and a little bit of algebra in order to find minima or maxima. And in order to do that, we're going to start transitioning, but I need to bring up this one fact, and so I wanted to notice it here. Let's draw the derivative, and I'll just tell you what the fact is. So if I was to draw the derivative, right, we have a technique for drawing derivatives. We first figure out where is the derivative equal to 0. So I would say here around 1.9 and here around 5.5. So 1.9 and 5.5. And then we would say, maybe in this first part right here, is the derivative positive or negative? And we can see that the derivative is going to be positive, right? The slopes of these little tangent lines, all the slopes are positive. They seem to be kind of leveling out here, but they're positive. So positive, kind of leveling out, right? The slope's kind of going towards 0, but they're all positive, right? So in this case, I'm drawing it above the x-axis. Positive numbers up here. Okay, now, in the next interval, we can see the derivative seems to be always negative. then it kind of levels out. So it's closer to 0, then it becomes more and more negative, and then it becomes less and less negative, and it heads back towards 0. So in this area, it looks something like this, maybe. More and more negative, and then less and less negative. Right? We need to hit those 2 points. And then finally, back over here in this third area, it seems that the derivative, the slope of the tangent line, is positive, and it seems to be getting more and more positive. So something like this. More and more positive. Something. Okay, so this is where our maxima is at 1.9. This is where our minima is at 5.5. And you can see in this graph here, these happen to be the places where the derivative is equal to 0. So the claim is, if you want to find minima or maxima, we should be very interested in where the derivative is equal to 0. So let's go ahead, next page. I've given us a theorem, right? So if f of x is equal to c is a relative maximum or minimum of a differentiable function f of x, then the derivative is going to be equal to 0. Okay, so again, right, relative maximum or minima, the derivative is going to be 0 there. That's basically what we showed with this example right here. Now a definition then, we become very interested when the derivative is equal to 0, so we're going to give a definition. A point x equals c is called a critical point of a function f of x if the derivative there is equal to 0. Okay, so these are interesting points, so we give them a name. We're going to call them critical points. And so I have a little bit of a warning here for us, right? All squares are rectangles, but not all rectangles are squares, right? You may have come across this in your favorite geometry class or something like this. So in our context, I want to say all extrema, which is a fancy word for minima and maxima, are critical points, right? The derivative there is equal to 0. However, not all critical points are extrema. So, let me go ahead and emphasize that here with this example. Show that x equals 0 is a critical point of f of x equals x cubed, and then we're going to graph it and show that it's not an extrema. So, okay, I'm going to show that it's a critical point. In order to show that, oops, I don't know why it's jumping around a little bit on me, but okay. In order to show that it's a critical point, well, according to the definition, we would need that the derivative is equal to 0. Okay, so let's take the derivative. Luckily, we can do this using the power rule, right? So the 3 would come down, and I'd have x squared. And I want to know, when is the derivative equal to 0? Well, if I was to solve this, well, first thing, I'd probably divide by 3 on both sides. And then I'd take the square root on both sides. And so technically, right, the square root of 0 is 0. Usually you would have a plus or a minus, but plus 0 minus 0, that's the same thing. So just x equals 0. So therefore, x equals 0 is a critical point. It's a place where the derivative is equal to 0. So x equals 0 is a critical point. I'm going to write crit point of x cubed. So we have a critical point. The question, is it a minima or a maxima? Or in this case, right, we called it an extrema, right? So if we graph x cubed, let me go ahead and pull out my calculator really quick. So on, forget, it's not like this. Let me go ahead and attach my keyboard really quick. Try to breathe life into this. All right, there we go. On, so y equals x cubed, and then we graph this thing. And you see we get something like this. So if I was to try to draw a sketch here, crudely, it would look something like this. Let's maybe even zoom in on it on our calculator and see really what's happening at 0. So I'm going to zoom and in. And so yeah, you can see at 0 here, it kind of flattens out, and then it keeps going up. So at this point, x equals 0, you can see it's not a maximum, right? It doesn't look like the biggest thing around. In fact, all the values of f of x over here are bigger than at this point. And it's not a minimum, right? It's not the smallest point around, because all the values just barely to the left of this point are smaller than it. and therefore, yeah, it's not a maximum or a minimum. So, x equals 0 is not a max or a min. Short for maximum and minimum, right? So, okay, just because you have a critical point doesn't necessarily mean that it's going to be a maximum or a minimum. So, which ones are, right? We need a test. So this right here is the test to tell us, finally, right, which critical points, we know we like critical points, which critical points are actually minima and which ones are maxima. So suppose C is a critical point, we found that. We have a nice continuous function f of x, nothing too crazy, and its derivative is defined close, for x close to and on both sides of C. Then we're going to determine the sign of the derivative to the left and the right of x equals c. This will make a lot more sense. We have a couple examples coming up. But here's the kicker. Part A, if the derivative is positive to the left of x equals c, negative to the right, then f has a maximum at x equals c. If the derivative is negative to the left of x equals c, positive to the right of x equals c, then f has a minimum. Okay, and then finally, if the derivative has the same sign on both sides of x equals c, then x equals c is neither a max nor a min of f, we'll say, or f of x if you'd like. Okay, so let's go back up here to this example really quick, and we would expect, right, since we don't have neither a max nor a min, right, we're probably in this case right here, but let's go ahead and kind of show you how to apply this test. So I'm going to use a number line here, and we need to be very interested around x equals 0, right? I need to calculate out the derivative to the left of 0 and to the right of 0 and see if it's positive or negative. So, okay, let's think about if I was to plug in a number, right? Here's the derivative up here. If I was to plug in a number to the left of 0, and the claim is any number will suffice, I guess, so like -1, -2, -3, -4, any of these numbers, when you plug them in, you can see, well, you're going to square it and you're going to multiply by 3. So you're going to see that it's going to be positive, right? So over here to the left of 0, it's positive. To the right of 0, so if you were to plug in a test point, right? So if I did a test point like -1 over here, I'll do a test point like 1 over here, but it can be 2, it can be 3, it can be 4, anything bigger than 0 in this case. So if I plugged in 1, for instance, you can see I'm going to square it. I'm going to multiply by 3. That'd be 3. That's, again, a positive number. But if you plugged in like 2 or 3 or something like this, the claim is, well, you're going to square it. It's going to be positive, and then you're going to multiply by 3. It's going to be more positive. So in this case, you can see the derivative has the same sign on both sides of x equals c. And therefore, we could tell by this test right here that we're actually going to have neither a minimum nor a maximum. So this is a way that we can do it without actually graphing, that just using our calculus and algebra knowledge, we can now figure these things out. All right, so I have a few more examples for us to really emphasize this, and then we'll be all set. So, okay, let's do it. Example 1.9, find and classify the critical points of this function here, x squared minus 4x plus 5. So first of all, find critical points. Critical points, again, are where the derivative is equal to 0, so that means, well, I need a derivative, right? So here we are, our calculus. Take the derivative. According to the power rule, this is going to be 2x, and then this is minus 4, and the derivative of 5 is going to be 0. And so we want to know when is the derivative equal to 0. That's going to give us our critical points. So I'm going to add 4 to both sides. I'm going to divide by 2, and this gives us x equals 2 is a critical point. Crit point. Okay, so the claim is, well, this is a critical point. This is a point of interest, right? Is it a maximum? Is it a minimum, right? Is it maybe nothing? So this is the part classify. We want to classify this critical point. And so I'm going to go ahead and use the same technique from before, right? I'm going to draw a number line, and my point of interest is here at 2. this is going to be mapping information about the derivative, right? So we want to plug in and find information about the derivative. Is the derivative positive? Is the derivative negative, right? One common mistake I see is people start accidentally plugging it into the original function. But no, we want to plug it into the derivative. All right. So if I pick a number to the left of 2, right? So like 1 or like 0 or whatever, right? If I plug that in here, let's see, 1. So 2 times 1 would be 2, minus 4, that would be negative 2. So this is negative, right? So there's a nice negative. Likewise, if you plugged in 0, right, you would get negative 4, still be negative, right? Anything to the left of 2. Okay, if I plugged in a number to the right of 2, let's say 3, right? So 2 times 3 would be 6, minus 4, that's going to be positive. And so now we go back to our theorem, which says, if you're negative to the left and positive to the right, in this case of 2, then f has a minimum, right? So, but I'd like to think about this logically really quick, right? Because I don't want you to have to memorize, I mean, that's a lot of words and stuff. I just want to draw this out, right? A negative derivative means that it's decreasing, right? It has a negative slope. Over here, a positive derivative means that it's increasing, that it has a positive slope. And so if you just draw a little picture here, you can actually see that you kind of make a minimum sort of deal. So x equals 2 is a minimum. Or if you want to be more precise, right, a relative minimum. So you found the critical points, we classified them. There we are. Okay, let's do one more here. Determine and classify any extrema, right, of g of t equals t minus the natural log of t. So you can see we need to remember a lot of our derivative rules here. Let me first of all remind us, right, so this function has a restricted domain, right? Natural logs can't take in all real numbers, right? They need t to be greater than 0 is domain. This will come up here in a little bit, but we're only considering positive t values because that's the only time that the natural log of 1 and the natural log of 2, the natural log of 3, it's the only time it makes sense. If you try to do the natural log of negative 5, your calculator will error out, right? It doesn't make any sense. Okay, so just as before, we want to find our critical points. So we're going to take the derivative and set it equal to 0. So the derivative of t is 1. The derivative of the natural log, well, that was good from 4.5. We know that this is 1 over t. And we want to know when is this equal to 0. That's going to give us our critical points. So let me see. I'm going to go ahead and add 1 over t to both sides. So 1 over t equals 1. Do a little bit of cross multiplying. That's going to give us t is equal to 1. And so there it is, right? T is equal to 1 is our only critical point in this case. So let's go ahead and plot it on a number line. In this case, right, remember, because our domain needs to be greater than 0, we're going to stop here at 0. And we're going to just go over here to, let's say, 1, right? That's our critical point. That's our point of interest. Again, we're mapping information about the derivative. So I'm going to choose a test point in here. I'll use purple again. I'm going to do something like 1/2, right? I can't go all the way to 0 because it's not in the domain. I'd be dividing by 0. That'd be a problem. So I'm going to do 1/2 in this case, right? And so when I plug 1/2 into, again, the derivative, let's go ahead and pull out our calculator here. It's a little bit of a pain. We have calculators. So I'm going to have, let's see, let's get back to my main screen. 1 minus 1 divided by, and then t is 1/2, so 0.5. So that is -1. So in the first case, we have a negative value, right? And now if I plugged in something over here, like 2 or like 3 or like whatever, right? Let's go ahead and plug that into our derivative. And okay, this one I can actually do on my own, right? 1 minus 1/2. 1 minus 1/2, that's going to be 1/2. The big thing here is that it's positive. So, as before, right, we had, this is decreasing. Now it's increasing. So x equals 1 is going to be a minimum. So I guess t, right? T equals 1. T equals 1 is a minimum. And if any point, right, you're not sure about these things, you can go ahead and pull out your calculator. So let me pull out my calculator here, and I can graph this, right? So let me go ahead and verify this, make me feel good. that this is x minus the natural log of x. And if we did things right, this should have a minimum at 1. So let's go ahead and graph. And indeed, you can see at 1, it seems to have a nice minimum. And let's go ahead and zoom kind of standard really quick. We had zoomed in from before. So yeah, it seems to have a nice minimum at 1. You can see, again, the picture doesn't make any sense to the left of 0, right? Because the domain here is t greater than or equal to 0. So anytime you're a little bit hesitant, you can go ahead and graph this to verify that you have the right answer. But I want to emphasize to you guys, right, we are in a calculus class. When you do this problem, I want you to show some calculus, right? Taking the derivative, setting it equal to 0, all this stuff. I want you to show the techniques that we're learning here in this class. So the calculator is a great way to verify your answer, but you'll often be graded on if you can do the calculus and the algebra to actually justify the answer, right? So in general, the answers are worth very few points. It's actually the full solution where you use calculus, where you use algebra, that I guess the points really lie. And that's the important thing that we're trying to get across here in this class. All right, thank you very much. I'll see you guys next time here in 5.2. We'll start applying these things to some more real-world problems. I'll see you then.